So friends, welcome to episode 4 of our story series on photoelectric effect. Last time we talked about Hallwachs experiment to qualitatively show that yes, when ultraviolet radiation falls on a metallic surface, the electrons that time electron word was not there, but essentially there is charge created, and those things were done, and we had done an experiment to kind of replication of Hallwachs experiment. And now today our hero will be a very joint personality, and that is J.J. Thomson, right? Sir J.J. Thomson is such a big name. Everyone knows, it's a general knowledge, not only science students, even normal audience also know that he was the person who discovered electron, and that was year 1897. Okay, so before that, atom was the final smallest unit, and people believed that okay, this is the last, there is no subdivision of that. But then a series of experiments by J.J. Thomson, and in continuation with what other scientists had been doing for long, and that was studying conduction of electricity in gases at low pressure. So those the whole thing culminated finally in 1897 when Thomson declared from his experimental data that all materials, all atoms have tiny particles in it which have negative charge, which have mass, and then he also measured E by m and all those things and established that inside atoms also you have structure. You have negatively charged particles which are very light as compared to the lightest atom, that is hydrogen. Okay, so these tiny particles had mass apparently some 1800 times smaller than the smallest, lightest atom, and these particles, which he called corpuscles, they were part of all the materials, so that was a big discovery. So if I go a little bit in that history, it starts with, let us say, Crookes, right? Crookes tube. Crookes was the person who used to make varieties of glass chambers, and is known as Crookes tube. And the basic elements in the Crookes tube are, you have some cathode, is a metal electrode, and this is connected to the negative terminal of a large potential difference, and then you have anode somewhere. You have anode somewhere, let's say somewhere here you have anode, and then you have from somewhere you have to pump out the air, so going to vacuum pump, from where you can reduce the pressure and so on. So when you reduce the pressure and apply high voltage between cathode and anode, then what you see is varieties of colors. First, varieties of colors appear inside this tube. But if you go on reducing the pressure, finally everything becomes dark and all colors gone. Right? So that's a separate thing. But everything is dark here. But this part of the glass, that shines greenish. This part opposite to this cathode here, that shines greenish, known as fluorescence. So if I talk in today's terminology, remember I'm talking the history, the story is much before the electron discovery, or those corpuscles as J.J. Thomson named that in his experiment. Before that, right, some 20 years before that, 1870s or so, these Crookes was there to study all the conduction of electricity in this low pressure environment, low pressure air or low pressure gas. So you have whatever is the residual gas here. So some ionization is there, some electrons are there, some positive ions are there, and because of this electric field, those positive ions will go this side and hit this cathode with large velocities because of the large mass. And then electrons will be emitted from here. So they are the main component. You do have electrons from that gas also, little bit, but main component is electrons are ejected from this, and these electrons go and hit this glass surface here, and there you have some excitation of these electrons in this material, and from there that greenish color is there. Alright, so in those times, 1870s and 1880s, this electron etc. was not in the mind. So people thought that something is emitted from here, and some people thought that it is some kind of radiation, some kind of light, invisible. Like we do not see light. We see using light, but we do not see light. Similarly, this is invisible. So it's something like waves, and that time waves in ether like light. So that was one group, one thought. Another thought was that no, they are massive particles, and there are particles which are emitted, and then they are coming here. Right, so variation of this Crookes tube was the main thing, and a very famous picture you might have seen in textbooks, that if you put a cross here, some kind of a cross here, if you put some kind of a material here, then on this other side, on this part of the glass, you will have a shadow of the same shape. You will have a shadow of the same shape. Right, and that part of the glass, there is a darkness on there, and the remaining thing is greenish. So on that greenish platform, you have a shadow. So something is going in straight lines and casting shadow. Right? So these kind of experiments were extended by J.J. Thomson, and then he found that yes, these things which are coming here, they can be deflected by electric field and deflected by magnetic field. So people were trying to study this before Thomson also, but then magnetic deflection they could see, but electric field deflection was difficult to see. Right? And then this J.J. Thomson found that okay, people failed to see the deflection by electric field because there was enough air here or enough gas here, the pressure was not that low, and then that got ionized, that became conducting, and that shielded these cathode ray beams from being deflected, and so on. So when he reduced the pressure to very low values, he found that it can be deflected by electric field, it can be deflected by magnetic field, and then from the calculations he established that it has certain charge and certain mass, and from that experiment that E by M could be calculated, and that was a characteristic of those corpuscles. So changing the gas, changing the cathode material, this E by M was all the time same, and from there it was established that okay, all atoms do have inside these kind of particles, identical particles, the whole of the world and all the materials and so on and so forth, and that was later named as electrons. So that is J.J. Thomson. When Hertz did his experiments on electromagnetic waves, and as a side result found that okay, ultraviolet radiation when falls on metal, then these sparks are easier to do, and therefore the conduction increases, and therefore some negative charges are there, so that photoelectric effect. And then Hallwachs and Hertz himself and certain other scientists also performed that, and J.J. Thomson also did that. He also did a separate experiment, and then showed that okay, if you shine ultraviolet light on this, don't apply any voltage, but shine ultraviolet on this cathode, and again those cathode rays are emitted with the same E by M ratio, right? So that is how he also confirmed photoelectric effect, yes, by shining UV light on cathode, electrons are ejected from there. Okay, so these experiments that I have described by Thomson, these were performed in the year 1899, and that is 2 years after that so-called discovery of electrons, where he showed that cathode rays, which were known for a very long time, are nothing but streams of particles having certain charge and certain mass, and the ratio of E by M or M by E, that he has calculated in his 1897 paper, and very carefully designed experiment. And this Crookes tube is the kind of starting point that I have just mentioned for each piece of that experimental work in 1897 and also 1899. For each piece of that research work, he has designed a new vacuum tube, okay, corresponding to the requirement of that piece of research. So excellent design and excellent fabrication, and then excellent performing the experiment. So the first observation of photoelectric effect was made by Hertz in 1887 when he was trying to generate electromagnetic waves in the laboratory. And then Hertz himself made a full-fledged experiment to confirm this, using again spark gaps and shining light on that. And in 1888, Hallwachs did experiments to confirm what Hertz had observed in his 1887 experiment. And J.J. Thomson's experiments that I had described were in 1899, 2 years after he had established that cathode rays are nothing but electrons, which are omnipresent in all materials. Okay. Now, I should mention at least one more scientist, a Russian physicist, who had done experiments on photoelectric effect in 1888 itself. So that is our another character of the story, M.A. Stoletov. This name, the last letter here is V that I see everywhere, but in that paper which is published in 1888, this is W. So I go with the majority and write it to V here. Now he was a Russian physicist, and he also did a simple experiment on photoelectric effect in 1888, but that was a bit more quantitative. Let me first describe his apparatus. He had taken two metal plates and circular discs of radius some 22 centimeter or so, and placed them face to face. Now one of the discs was a solid disc, and another was not a disc as such, but it was a wire mesh. So this is that solid disc, this is that solid disc, and then in front of it another disc which is actually conducting wires, these kind of wires, wire mesh like that. And then he connects this to battery, alright, and battery he makes that just copper zinc type of battery, Daniel cells, but then 2 plates, 3 plates, 4 plates, many plates, 100 plates and so on, so varies that. So this is cathode, the solid one is cathode, and this is anode. So the negative terminal of the battery will be connected here, and the positive terminal will go to this through a very sensitive galvanometer. a static galvanometer, we say, and the sensitivity is of the order of say some 10 power minus 11 amperes or so. So when galvanometer deflects, one can measure how many divisions it is going, and from there one can measure the current. Then he shines UV light on this using an arc lamp. Alright, so let us say this is an arc lamp and it gives you light which has UV component. Of course, other lights will be there. So this is arc, right? This is arc lamp. So this is the kind of setup. This circuit is open here, air in between, and no vacuum or other thing is reported. So it's again a simple setup. What he finds is this light goes through these gaps and falls on this material, on this metal, on this disc, solid disc, which is the cathode, which is placed at a negative potential with respect to this. And then when this arc shines and the light falls on this, you have a current. That's the photocurrent. This arc has some UV component, and that UV component falls here, and then there is a current. Now we are calling UV all the time. It doesn't mean that only ultraviolet can cause this kind of emission of electrons from here. Right? It all depends on what metal it is. Generally, the metals which are used in these experiments have this character that visible light is not able to eject electrons from here. We will talk more about it once we complete this series, and then we go to the Einstein's explanation. There we will talk more about all these properties. Nevertheless, this observation was there, and then he studied several things. In this particular piece of experiment that was reported in 1888, he has done several things. One is that putting a screen here, putting some kind of shield here, right? Some kind of shield. So you find that if it is an opaque sheet, of course, the entire light is blocked, everything is blocked, it's opaque, and then there is no current or negligible current. But then he puts varieties of glasses. So the light is going, but even then the current is very, very minimal. And then when he puts quartz, then he finds a very significant current. So we have already talked about it. Quartz does not absorb UV, right? Quartz does not absorb UV. Normal glass will absorb it, and therefore normal glass, although it is transparent, it will stop UV, and since this metal here is not appropriate for ejecting electrons with visible light, there is almost no current. So that was one thing, that UV light is needed to take those electrons away or to create that charge. Okay, 1988. The terminology should not use electron as such. Okay, so that was one observation. Then the second observation was on he blocked part of the surface of this disk. He blocked part of the surface of this disk and exposed only remaining part, and found that yes, the current is proportionately diminished. So that's another part. And then the third part was that separation between these plates L. So he studied the current, what the dependence on the current on this separation. If you increase the separation, what happens here? So he says that the current decreases as L is increased, current decreases. That one can understand very in a simple way, but not inversely proportional. And this I is something like E divided by A plus BL. This time, what is E is that? This EMF which is applied across this capacitor. Right, so that is another set of results that he says. Then he talks of dependence on the current on this EMF E. So that's a very significant part. If you increase this EMF, and that he has done by putting several plates in that battery, and so if you increase this E, how does the current go? So that for that he says that okay, initially when E is small, when this EMF is small, then initially it's almost proportional. It increases, right, proportionately. But once it assumes some larger value, after that the rate of increase of current is slowed down. So he has not shown any graph, but if I show on a graph, it will be like if this is E, then it will be something like this, and then it tapers. That we know when we do. I'll talk more about this. If you increase this EMF here, then the current finally saturates. We will talk about it. Finally saturates, so it's going towards that. So these are the observations in one particular paper which I could find in English. There are 3 or 4 or maybe more papers in the same year or a year later on photoelectric effect, where he must have measured other things, but those are not, at least I could not find them in English, could not understand. They are in French and so. But then something called Stoletov's law of photoelectric effect, okay, and that must have come from those researches that he has done, and that is this current is proportional to intensity of this light, this UV light, right? So intensity of this the source. In this experiment also he has taken different materials to produce this arc, and has established that okay, aluminium is the best, it gives largest current, and other materials are giving different kinds of current. So it depends on what material you are using, because different materials will give different wavelength distribution of UV, and therefore the current will depend on that. So maybe he has studied it more systematically and has established that the photocurrent, this current here, is proportional to the intensity of the light that is falling on that, and this is sometimes called Stoletov's first law. Okay, now this is significant. I chose this one because I came across it, so that was one. And second thing is, Hertz has done just he has mentioned that it is there, and even his next paper where he has done this research on this part only, there also he has not made much of data collection, quantitative data collection. He is busy in showing that yes, the spark length increases, decreases on this UV, and the length of the spark little bit gives indication, but measurements are still missing. Hallwachs, of course, is no measurements, but this one, they are all 1988, and even that Thomson paper of 1899. There also the main focus is that these charges which are generated when ultraviolet falls on a metal, so those are same as cathode rays. Okay, the main focus was on that. He is measuring electronic charge E by m, and then showing that okay, the cathode rays which he had been studying for so long, the values of the parameters there and the values of parameters for these charges which are coming out of metal on UV shining, they are the same. So the main focus on that. So in that reference, this particular Stoletov's result, where quantitatively he is measuring things and giving results, is a good contribution in the story. All right, so that is it, and then maybe next episode we will talk of another giant personality, 1905 Nobel Prize awardee Philip Lenard. It has given very good quantitative results, and Einstein in his Nobel Prize work has mentioned about this.